kind of how to aim what we're going to discuss. Right, so that if you hover over the bottom of your screen, you'll see the chat, and then you should be able to.
So we have a lot of no's. So I used it a few years ago.
So right now I can see I'm looking. Oh, Paul. Yeah, Paul. I think I recognize the name. There's several names that I've recognized there. Okay, and Ryan answered the next question that we that I'm curious about. I'll ask everybody.
Okay. Some people
Okay, that's great.
Yeah.
Yeah. So the next question I wanted to find out is what subject area people teach. Biology teacher got in there first. Oh, pre-service teacher, great. Okay.
Oh,
well,
nice.
Yeah, we can talk about that especially. Okay, so we have pretty wide mix, so that's great. We can talk a little bit about sort of generally what you can do with Pivot Interactives, and then we'll look at some examples for each of those subject areas. So okay, so I'm going to go ahead back and share my screen, and then if you would like, you can keep asking questions on that chat. I won't be able to see it, but Tiffany will, and so we'll kind of go back and forth, because I'll probably forget things along the way, and you'll have questions. So your questions will make this better. So please ask away. So Pivot Interactives is, I'm a teacher myself. That's what my career has been for the past few decades. And I wanted to figure out a way that I could have my students interact with real data and real phenomena and real events without always having to set it up myself. I wanted my students to be able to do that on a nearly daily basis. So probably a lot of you have noticed that we spend a lot of time drawing pictures and writing paragraphs to try to get these models and these situations, make them concrete for students, and it's tough. And when we want to demonstrate something, it has to fit in our class and the amount of time that we have in our classroom budget. And so our goal was to make this library of events that would let students explore science sort of in a different way. So let's see, I'm just going to look at an example here. So let's just start with a chemistry example. So in chemistry, this idea of using the mole concept and stoichiometry to describe the amount of a substance and sort of switch back and forth between molecular formula and the molecular weight and the grams. It's one of the things that we want students to be able to practice. And so this is a lab that all chemistry teachers that I've talked to do some version of this lab where you take an amount of substance and put it on a scale and then heat it. In this particular case, you can actually hear the sound. And there's a very precise scale. And so now we heat this substance, can watch the change. So they wouldn't be able to see that normally because you don't want to have them putting the face right up to a Bunsen burner. And then it gets heated for 5-minute intervals. We can slowly see it changing. So this process would take, if you did it in the lab, 15 or 20 minutes of going back and forth and doing this. And so it's an interesting balance. Yes, we want students to learn how to use a scale. Yes, we want them to have experience with a Bunsen burner, but that's probably not the core of what we're trying to teach them to do. The core of what we're trying to teach them to do is to be able to use these observations and then this data, understand what changes are happening here. And so here we step them through, we ask them to apply these ideas that they're using, like just measuring the difference in mass. So they can click one of these and see that that's not right, and so they get feedback about why. And this particular one steps them through the process of using the mole concept to understand what's happening here. So then after they do that, I'm going to jump you down to, we give them a lot more freedom. So now we say, here's a situation where you have multiple substances and multiple trials. And here the students can select which substance and which trial. So you can have different students analyzing different scenarios. And here we ask them a different question. If we tell you the number of hydrates of water that are attached to this salt, can you identify which substance it is? So it kind of flips it around and turns it into sort of an open-ended problem solving. I'll just show you this one last part because I think it's kind of cool. One thing that we always really want to have our students do is be able to understand what happens if something doesn't turn out the way you think it's going to, right? Like if you have a computer simulation, then everything comes out perfect all the time. But in lab, very often for very interesting reasons, things don't work the way that you think that they're going to. We really want our students to be exposed to those. So in this case, we have two trials, both of which the students are asked to predict what they think the outcome is. And in both cases, their prediction is wrong. In all the previous ones, their predictions come out really nice and close because we were just really careful. But this time they come out wrong. And the reasons are really interesting. In one case, we didn't heat the substance enough. And so you can see that the color never fully changes. And so we don't get all of the water of the substance. In the other trial, we heat it so hard and so long that the substance actually decomposes. So you end up with these two different results. And so that would be so tough to get that entire process done in a class. And yet we've tested this with students in one class period or one homework assignment. They can make their way through the whole thing. So I want to stop there for a second and see what kinds of questions people have so far, and then we can keep going. Tiffany, what are you finding? What are people wondering?
I think they're taking it all in right now. Nobody
okay. All right. So that was an example of one in chemistry. Let's look at a physics example. And okay, so then I should also back up and talk a little bit about the logistics. So Pivot Interactives is a subscription-based service. We worked very hard for a few years to see if there was a way that we could do this for free, and we can't. And so we switched over and we work with a company, Vernier Software and Technology, a really well-known company for science teaching equipment. And they are the distributor for this, and you can buy subscriptions, and it's normally $5 per student per year to buy this. But because of this crisis that we're in, we have two ways that we're offering for teachers to access it for less money than that. One, you can do a 30-day free trial that you can use with students and teachers, and you can have access to all of the content and all of the features for 30 days. And so if you haven't used Pivot before, you can absolutely use that to kind of bridge the gap, hopefully bridge the gap mostly to get all of the kind of lab-based learning that you want for your students. But if that's not enough, we also lowered the price to $1 per student to buy seats that last through the end of this school year. And we really looked at whether we could do it for free, whether it was possible for us to just say, why don't we just open the doors? Because I know a lot of companies have, and we just found that we can't. The cost for us to host it is just a little bit too high for us to be able to say, okay, world, have at it. And the amount of demand that we're seeing now, we think we made the right choice. We think $1 per student is pretty affordable for most situations. And that's allowed us to keep this whole thing under control and keep the platform working, which has been a challenge because our usage is enormous right now. So 30 days free, $1 per student for the rest of the year. And then if you decide you like it and you want to use it in the future, then it's $5 per student per year. And those, by the way, are all high school prices. College prices are higher, $10 per semester for college use.
Hey, Peter, there's a couple of questions. So someone asked, does the score go down with each wrong guess? So I guess that's when they were making the predictions.
Yeah. No, it doesn't. We don't have the ability to have it decrease yet. But that ability to add feedback and automatic answer scoring, we're working on expanding that a lot. And so you'll see, we're still relatively new. And although the platform works great the way it is, we're making improvements to it all the time. And mostly what drives that is what do teachers want. And so if teachers are like, yeah, we really want the ability to have it decrement the score with each wrong attempt, we would add that. I'll tell you, in a lot of cases, those multiple choice questions are meant to teach the students how to use it, like to step them through so that they know how the process works. And then we give them a much more open-ended question. And that's really where you want them to do, like, if you're going to score, that's often what I do. Like, let them do the multiple choice one, maybe give them enough attempts in the multiple choice that they can get them all right. And then it's like, okay, now you understand how this works. Now let's do something creative with it in the second section.
Okay. And I see you have the blow dart collision up, which feeds to a great question here, or I think will segue nicely. So it says, how does a teacher assign different parts of the lab to different students or to groups of students?
Okay. So right now it's a one-to-one. So what happens is that you create a class. I'll just quickly go through how you do that. We have this page here, and you set up a new class. You give it a name. You decide whether your institution is going to pay for it, which means you're going to buy seats through Vernier, our distributor, and then you're going to have the seats in your account so that the students can use them. So if you have 30 students, you buy 30 seats. So that's what we mean by institution purchase. But we also have it set up, and this isn't right for most high schools, but a lot of colleges work this way, where if you click student, then when the students go to join, it'll prompt them for a credit card. And then if you do that, then in either case, the instructor themselves doesn't pay. But here, like, your institution is paying for seats, here the students are. And then you select whether it's high school or college. And then once you do that, you'll get a class, and there's an activation code, a class key right here. And you give this key to the students, and then they go sign on, create themselves an account, and they'll be automatically populated into your roster like this. So that's how you build a class. And then to assign an activity to them, you go into our library, and there are hundreds and hundreds of activities in here, and you can search by what subject area you teach, or within that subject area. So I worked my way down to physics, and then impulse momentum was the one we were looking at. And then I can choose from amongst those. And so when I find one, I'd add it to my library because I want to use it myself as an instructor. And then once it's in my library, that's where you can then assign it. So now you can just go here and say, okay, I want to assign this to whichever of my classes. So I'm going over it pretty fast, but we have a lot of documentation, and I think in general, it doesn't take teachers long to go through and set up a class, find an assignment they want to give, and assign it to their students. Did that answer the question?
I think so. I think he's wondering how different kids can do different, like, trials.
Right. Okay. So we have that ability too. Yep. So I'm going to go back to.
Is that correct, Brian? Okay. Yeah, he said yes.
Okay,
like how,
great.
Yeah.
So let's look back at that impulse momentum. I think I misunderstood the question. So for blow dart cart is an example, and there's lots of activities that we have that are like this, where there are multiple trials. In this case, 11 different trials, and they all look basically the same. Let's look at this first one first. So this one is just a pretty standard collision. It's kind of cool looking, where this blow dart comes out of the pipe. There's a person on the other side, and they blow a puff of air into there, and the dart thunks into this cart. And the measurement tools that students have here are this interactive ruler that they can position where they want, and a stopwatch. So now the idea when they select one of these trials, so finally I'm answering the question. So you would, in this case, you'd say to the students, okay, I want you to do trial 4 and you to do trial 5. Divide them up so they're working on their own trial and maybe working together with a partner. But for all of these trials, they only see the beginning of the collision. So the blow dart comes out, but pretty much once the dart sticks into the cart, that's the end of the video. So here we're going to ask them to make a prediction. So they're going to put the ruler up here, reset the stopwatch, and then just maybe time how long does it take it to go, some distance like that. And from that and these masses, they should be able to predict how fast this cart is going, but they can't see the rest of the collisions. They don't know if they're right. So they go through here and enter their answers. And then to be able to see the rest, see the outcome, right? So this first part is just like any word problem. Well, if I know the velocity and the mass of the dart, then I can predict how fast the cart's going to go. But what's cool here is that after they make that prediction, then they can lock that first part so they can't revise it, and then go down here and choose the same trial. But now they can measure the outcome. So we find with students, that's way more interesting. Like, okay, I answered this textbook problem. I have no idea if that's really what would happen in real life. And so here they do. They can measure the speed of the cart. And then they again have these discussions about, well, how close was your prediction? And what kinds of things would cause your prediction to be off, and in which way? So in this activity, we actually spend the majority of the time talking about possible reasons why your prediction would be wrong. That's a really fun one. My students really like this one. And I think this one also could be pretty easily used as a quiz. So you're like, okay, because this doesn't teach them how to use momentum. This allows them to apply the idea of momentum in collisions.
Yeah, and so outside of pivot, you would want to instruct your students on which parts that you want them to do, or can you can.
Yeah, you could do that. Outside of pivot, you could do that. You also can change these. So if you have an activity like this, you can go in and edit it. And so if you want to split it into two activities, you could have them do different parts, or if you want to ask other questions. So let's say, for example, that you think that those questions about discrepancies between their prediction and the result, like if you decide you don't want those, you can just delete them. So you have the freedom to kind of change these activities to match your teaching style or where your students are at. To kind of match it to what your needs are.
Mm-hmm. And I used this one in class last year. We did it. I feel like they already knew how to use pivot at the point that I used this, but we did a lab investigation, and I had them do like the first 4 trials or something. And then we actually, when we took our quiz, like later in the unit, we used pivot to take the quiz, and there were 3 different options. And at the top, I just said which trial they were supposed to analyze for their quiz.
Right.
And so, and it was, since there were so many, I could choose 3 different ones that we didn't even use in the lab, but they were still comfortable and familiar with it.
Right. So they knew the process of using the ruler and stopwatch, but they were doing it on a new scenario that they hadn't done before. Yeah, I think that because you probably don't want to have them be confused about these tools during a quiz. You want them to show you that they know how to do the analysis. Right. Yeah, that sounds like a good idea. Yeah, go ahead.
Are you moving into something different? I was going to ask if you would show like a biology one, or unless you wanted to show another physics one.
The one thing that I would like to show in a physics one, but although it's actually, I can do it in biology as well. So we'll do both at the same time. So colored lights and photosynthesis. Man, was this ever an interesting one? I'll tell you who learns the most from Pivot Interactive is me, because I did not know any of this stuff when we made this. So here's one where this would not be their first experience with photosynthesis, unless it was maybe an AP bio class or something like that. So what we have here, the idea is to do an investigation to see what color light, how do different color lights affect the rate of photosynthesis. So we have this video where they can view it in under white light, and you see that it's time lapse. So you see how fast the clock is moving, and then you can see that the plant is moving as well, because plants move, which I didn't really know. And you can see that this level of carbon dioxide gas is going which way? Oh, it's going down, right? Because photosynthesis, that's what plants do. They use carbon dioxide. And so the students can make a graph down here, and so they can say, like, here's time, and here is CO2 concentration. And then they could put something like minutes in this, and then this is parts per million. And so then they can very quickly make a graph. And in this particular case, like they can literally go like in 15-minute increments, right? And so very quickly they're building a graph that they can use to see what the rate of change of that carbon dioxide is. And so in all these activities, you can say, I want to see what sample data would look like. And so here we have, you can see all of the different lights. So this pink one here is how fast is the carbon dioxide decreasing with this 7-watt white light bulb compared to this 8.5. So sure enough, you can see, ooh, there's a cool thing right here. Okay, so the slope is steeper on this one, right? Because the brighter light causes photosynthesis to be faster. Look at this last data point. See how like it's this really, really nice pattern. So if I click to unselect that one so that it's not part of the linear regression, these ones fit beautifully. What happened down here is that the carbon dioxide got so low inside that there was no longer enough oxygen to conduct photosynthesis. So you see this decrease in rate. And so that your more advanced students will notice that it's really cool and it's in there. Right, so this is, and then they can, I'm not going to go through this whole thing, but they can then compare that, for example, with green light, the photosynthesis basically doesn't happen at all. So you see almost no change in the carbon dioxide level. In fact, respiration kind of dominates. You see more of a increase in carbon dioxide rather than decrease. And so then we kind of let the students go through and learn a little bit more about light absorption by pigments, and they get to analyze. We extract the chlorophyll out of the leaves, and then they can compare the absorption spectrum for the chlorophyll. So that's the absorption spectrum from the chlorophyll to the spectrum of these lights, and see why each light produces a different amount of photosynthesis. So besides showing a biology one, I wanted to also show the data table and graphing. That's built into a lot of Pivot Interactive's activities, and it really helps teach students graphing, data collection and graphing and experimental design. I feel like I'm going too fast. How are we doing?
You're doing good. Now, as students are working through, they can save their progress, right, and come back?
Yeah, it automatically saves as they go. Every time they click on a data table cell, every time they click a multiple choice answer, as long as they hit that submit button, every time they type in an open-ended response.
Okay. And I noticed,
yeah, then it saves that as you go, and then as the teacher, you can go up to your class and look at all of the student results and grade them. We have some really nice tools so that you can grade them quickly.
So what is the range and mean for an average time needed to complete one of these modules? It probably kind of depends, huh?
I mean, so that's a really good question, and I can tell you that it is a wide range, and that's okay. I mean, because we have some, like there are some where they are really intended to be a 10-minute long. I want you to make an observation about what happens in this scenario, and you want them to do that just so that you can set the stage for something new that you want to talk about. So it could be 10 minutes, and then something like our Newton's second law investigation, which is allows students to develop the model for the relationship between what happens when you change the mass and what happens when you change the force, and kind of do it through a modeling style where they're designing their own experiment and collecting the data. The way I do that in my class, it takes about 3 days of class time, and that's including in-class time where we design the experiments in class, and then they go home and collect the data. So we do sort of a flipped lab. It's a really effective way to help students learn to collect and analyze data. But so 10 minutes, 3 days. And you can get a sense of that when you look at them. Like this for an AP class, when we tested this is like one good solid long class period for them to do this. Or you could have them again do the data collection at home. So do the first, kind of introduce it, then have it say, go home and collect the data. Tomorrow, we'll do the interesting part where we'll kind of look at what these patterns are and together explore kind of what's the underlying mechanisms that are making this show up the way it does in the graph.
So within a 30-day trial, as a teacher is kind of checking that out, can they assign some of these to their students?
Yeah, there's no restrictions during the free trial. You can have an unlimited number of students, and your students can work on the activities, and you can grade them. You do everything exactly the same as if you were a subscriber. A lot of times people think, and we're working to try to make it clear in our platform, sometimes people think that like, oh, as a free trial user, I can't create a class or assign things. You absolutely can. Use it, especially now, right? That's one of the reasons we're happy that the free trial exists. Like,
Yes.
use it as much as you can.
And could you show us like the list of activities that you have? And
Sure.
There's a question about if you could find it online somewhere, or if you have to go ahead and like start a free trial to be able to look at everything that you have to offer.
Yeah, that's a good question. You can find it without doing a free trial. So I'm trying to think of how I can show you that. I can, it'll only take a moment. So if I log out and I just go back to the regular Pivot Interactives page, then unfortunately it's a little bit hidden, but I'll show you that if you go under Learn More and then down to, so this is just regular www.pivotinteractives.com. Under Learn More, there is the Pivot Interactives library, and that's exactly the same once it loads as the library if you're a paid user. But on these ones, when you click on it, it won't play the video. So everything else, you can see right? It shows you what the video is going to look like, but you just can't use the activity. So that's a great way if you're like, well, I'm not sure whether you have stuff for the topics that I'm working on. So here are your category search. I should have pointed out that if you're an AP teacher, you can also do by AP content area, and then also NGSS standards are aligned in here as well. So take your pick of how you want to search it.
Do any of your, I think I know the answer to this, but do any of these require any kind of calculus knowledge? Or is it?
Yeah. I mean, there's none. No, that's not true. There are some, especially in the electricity and magnetism, where they do have to. Okay. They have to use calculus. Yeah.
Okay, but most of these, or I shouldn't say most, many of these could be scaffolded or like used at the middle school level, correct? Just.
Yeah, that's an interesting question. There's two things. First of all, there are pretty strict legal restrictions that we have to abide by, and so we do not allow students under 13 to use the platform.
Okay.
So that's, yeah, pretty important because there are specific things that we have to do with data for 13-year-olds and parental consent, and we can't adhere to those. So please don't use it with students that are younger. But then kind of when you get sort of in the 8th grade or even 9th grade level, the instructor should look at it and say, like, you're a good judge of where your students are at, and see what kind of modifications. There definitely are ones that can be done by young students. Like this is an example of one for, oops, now I have to log in. So there really are ones that can be done by young students. Yeah.
Okay. There was a question, somebody already has a subscription for 40 students. Can they access the free trial option to have additional classes?
They should just write to us on the chat. When you're on our website, there's a chat bubble, not for me because I'm logged in as an administrator, but there's a chat bubble down here. And then just send us a note and say, here's what my situation is. And we've got 3 or 4 people that are on that chat, responding to that chat all the time. We're really trying to find a balance. We want to provide as much free as we can, and we're trying to stay afloat, right? Meaning be able to, we know if we just open free trials to everybody, it'll sink our ship, the cost and the amount of strain it would put on our network. So we're just trying to figure out where's the balance. So just write a note on there and we'll find a solution for you.
Okay. Okay, this looks good. I think keep rolling. We're answering questions as we go, so it's good.
Okay, great. I saw a couple people had ones about earth science, if I remember seeing that. So
Oh,
I
yeah.
want to show that we have some really nice earth science ones. So this is one about how different gases respond to different sources of light. So we have, and this is an example of one that can definitely be done by younger students. So here we have one where Amal, and it's kind of nice that, like, you'll see in these videos that the people in them are all students. And so here's Amal, and she's taking these different gases, and she's just showing that no matter which of these gases you use, they're transparent. You can see through the gas, whichever gas it is. Right, so the idea for students is just to recognize that these gases allow visible light to pass right through. But if we then take them and try that with infrared, there's a very different result. So here we have a heat plate, and we are recording it using an infrared camera and a standard camera. And in this first one, we just take that same plastic bag, and it's filled with air. And we can see that the bag blocks some of the infrared light. And so we have a little measurement tool up here that the students can use. So this end of the scale shows this, the white would be that there is more infrared light. And then as we work our way down here, that's less infrared light. And so for this, we see we're kind of in this yellow, red, orange range. So some of the infrared is blocked. Then if we go down and choose a different gas, if we fill that bag with carbon dioxide instead, we already saw that in the visible spectrum, you can see right through carbon dioxide. It doesn't make any difference at all. But we can see that in the infrared, it is different. So now instead of being in that orange red range, now we've moved down into here, so we can see that there's more infrared light that's blocked. And so we can work our way down to these other gases. So I'll put this one here. This is a refrigerant used in automobile and home refrigeration. I'll move this out of the way.
Wow.
So you can see here that this blocks a tremendous amount, even though it's still a clear gas. It blocks a lot of infrared light. So this is not quantitative. Students don't have to know any math. They're just making observations about how these different gases look different when you view them in visible versus infrared. And it's a really important part of the greenhouse effect. And then we have more instruction here about, well, what are these gases? Where would I find those? So we have a little table that describes what these different gases are, and then let students compare in terms of climate change, which of these gases, we asked them to kind of explore that would have the greatest effect. And it's kind of neat, again, a thing that I learned is that one I showed you that appeared to be terrible turns out not to be very bad because it has an atmospheric lifetime of only 12 days. Whereas all these other gases last in the atmosphere much longer. So this actually turns out to be a really good choice for refrigerant because it doesn't last long and therefore doesn't have much of an impact on the environment.
A couple of questions. One, I see when you click lock answer and continue or something. So once a student clicks that, are they able to go back and edit anything that they have put previously?
They aren't. And so you always, as the instructor, you always have the option of turn it off. So if you don't want your students to have that feature, it's completely up to you. So you can see right here, so I opened up part 3, and there's a button here that says require this section to be completed before the following section. So you just unclick it.
Okay.
And now it won't do that. So you decide whether you want the students to be required to write an answer down and commit to it, before they open the next section. I would say that there are times when two teachers might be using the same activity, and one teacher wants to use that and the other doesn't. So you can just go in and decide for yourself.
Okay.
If you do have that checked, and a student just like, oops, I made a mistake, can you unlock that section for me? You can. You can go into your My Classes and click on, I don't think I have one that has a locked section, but you would be able to click on a student and scroll down to that student and then just click on the bottom of that section, unlock it for this student, and then they could go back and continue to work on it. So you can control that either on the assignment level, so it affects all of the students, or you can lock and unlock it for one particular student.
Okay. And I know that you guys are adding more and more as this goes on. There's a question, are you specifically going to have things on like gravitation, Newton's law of gravitation, orbital motion, Kepler's laws, things that are very hard to model in the classroom physically?
Yeah, the answer is yes. At the same time, I think that we also are aware of what are the strengths of interactive video and what are not. So for example, as a teacher myself, I love using Pivot Interactives for circuits to model how real circuit elements work, right? Like what happens when you change the voltage on a light bulb in real life. So you can see, or if you're an AP teacher and you want to talk about like resistivity, like we have examples like that. But I'm also really a fan of simulations, when simulations can show things like, for example, it's really tough to beat PhET's ability to show how the motion of electrons works as they pass through a circuit. And similarly, if you want to show like the shape of orbits, you have to beat simulations for that. At the same time, we think that in all these cases, there are places where interactive video can work, and it has specific advantages. So we do have some ideas for how we can do gravitation that you'll see in the coming years.
Okay.
But I think it'll always be true that there are places where like it's a balance, and I wouldn't say like, oh, if you had Pivot Interactives, you'd never want to use simulations, like, or you'd never want to use hands-on. Like for sure, this is a part of your teaching.
Right. Okay. Could you have a circuit one in here? Could you show that?
Sure.
I haven't seen any of those.
Just for like DC circuits?
Do you have anything, whatever you
Sure.
feel is the best one to show?
So depending on the level of, so it's probably a relatively small number of teachers who have to do RC circuits and RL circuits. So like a capacitor and a resistor, or an inductor and a resistor. I will say that this inductor resistor one was really, really fun because we wanted to find an inductor resistor combination. Sorry, we have to look at this just for a minute, because it's cool even if you don't ever have to teach. So wanted to have an inductor that had low enough resistance that we could see how it looks, and so we immersed the inductor in liquid nitrogen. So the inductor is sitting at a very, very cold temperature, just so that its DC resistance would be low enough that we could explore its behavior in a situation where the whole circuit acts slowly enough so the resistance is low, so the inductance dominates. So at any rate, the reason I point that out is not because, oh, okay, now I understand how an inductor circuit works, but it's an example of how we can modify things to make your students be able to see something they normally wouldn't be able to see. So if it means we're going to take a circuit component and stick it in liquid nitrogen, great, we'll do that. Probably wouldn't want to do that in your own class, but we don't mind. But this is the one I was thinking about. This is a more common, like, okay, I want my students to working on DC circuits. So here they can choose from different circuit elements, starting with a resistor, and they can very clearly see how the circuit is laid out. and then they'll watch that somebody is just going to come in and turn on the power supply and slowly increase the potential in the power supply, and so then they can read that current and voltage. And so then here they're going to make a data table, and we can look at the sample responses for that. And so this is about, again, about graphing, right? Being able to use a graph, use these current and voltage readings, and then be able to tell something about what does this line tell us? Is this equation useful in some way? And how will it look different if I use an incandescent light bulb, right? It's in the incandescent light bulb, they can see that it just doesn't fit a line, that you don't have a linear relationship between current and voltage.
Okay. Is linear regression the only option that they have?
Right now, that's a summer project that we will add other equations that they can use. One question I have, and I can put this in, and if you feel strongly about this one way or the other, we hear from teachers on the one hand, oh, we would love to have something more than linear regression. We also hear, well, what we like about linear regression is that it forces the students to find a function that they can describe using linearization. And it doesn't give them the option of doing, like saying, oh, I'll find a 7th order polynomial that fits. And so then they're like, that's it. I've discovered the mathematical law between current and voltage. It's a 7th order polynomial. So what do you all think about, should we have, this wide palette of functions that they can use? Or should we limit it? Or should we give you the option of both? So you can decide what functions do you want to have available for your students?
So there's a comment that says, as an AP Physics 1 teacher, I appreciate that linear is the only options. So there's the only option, so students have to learn linearization. As a physics teacher, I almost wonder about an inverse square, like an inverse or an inverse square relationship. I don't know what that would look like.
Well, you could still linearize with it, so you could make a calculated column. I should have pointed out when we looked at this that our calculated columns are extremely easy to use. And this is one advantage of being a teacher myself, is that we tested over and over again with students. So the way you make a calculated column in ours is that you click on this to add a new column. And so we have a column over here that's current in milliamps, right? So if I just wanted to make a current, and I want this one to be in amps, when I go to the formula, it's modeled after a calculator, because as we were testing it, every time we came up with a new interface, if the students didn't like it, they would pick up their calculator and start putting numbers in. And I would say, why are you using your calculator? And they say, because we're so comfortable with it. So we're like, okay, then we'll just make this. So I want to do current. That's the one that's already popular. So that's the 1 in milliamps divided by 1. So it's just the same way they would see it on their calculator. And so what we find is that the students don't, once they see this, they don't need any more instruction about how to make a calculated column. They will figure it out briefly, or they'll ask the person next to them. Not during coronavirus, but during normal times, they would ask the person next to them and they'd get it figured out in 2 seconds. So yeah, so they would have to make a calculated column here that says, I want it to be, 1 divided by current squared. And then they could linearize, plot that and see whether that produces a linear function. And they'd say, okay, that must be an inverse square. I fall on the side of wanting both. I think it would be nice to, as an AP1 teacher, I agree. You want them to rely on linearization because that's what they're going to have to do on the exam. But like I was looking at the APC exam from last year, and they had them fitted to a quadratic. So I think it would be nice if we'd say, like, what function do you want available for your students? And so if in this edit mode, I think it'd be really cool if you could just look at that and say, I want them to have, so this is the data table and graph. So you maybe have a thing over here that says linear inverse square, logarithmic, right?
Mm-hmm.
Whatever functions you want, and then those would show up
Because
for the students.
just as a side, like a teaching note, if somebody can linearize something, it doesn't mean that it always makes sense to, and
True.
just because it looks good, you know. And so maybe helping students understand that, yes, I can make this linear, and what does that mean when I do that, and
Right.
is that true? Like, is it always going to be true that, do you know what I'm saying?
Yes, absolutely. If it fits just because it fits, that doesn't
Right.
mean that it makes physical sense.
Sense.
That it fits. Absolutely.
There was a question that, do you have a way to manage significant digits? So as you were calculating those columns, there were loads and loads of numbers coming up. And, and
The answer is no, we don't. But when we redo our data table and graph, we will have something that allows you to do that. At least it's nice that the only place that they will see those is in the data table, but on the graph, you sort of can't tell how many. But yeah, it's a good point. We will have it. We don't have it yet.
Okay. And then Brian asked, can you do linear fit forcing of B equals 0? So
yep. Well, forcing, no. You can show the origin. You can decide whether to show the origin, but no, you cannot force force it to pass through the origin. But we'll add that too. We kind of, I mean, that graphing tool is one of the things that we did early on, and it's ripe for revision. And one thing that's nice about web software is that we will build it backward compatible with everything that's already there. So once we update it, like all your rest of your favorite tools will be there, and it'll just be a magically better data table and graphing tool. I think that's for September. We plan on, by the time you're in the fall or wherever we are in the fall, we'll have the new data table by then.
Okay. I don't know. It's about 10 till 5. I don't know if you have something else you want to show, if somebody wants to see something else.
Yeah, I think it'd be fun if there's a subject area where you're like, oh, I'm really curious about, like, how would you teach that? Like, what's a subject area that you really wish you had a better way of demonstrating it to the students, or a better lab? I would be happy to do that, or any other questions that people have.
I really liked seeing, and I'm not a biology person, but I really liked seeing the time-lapse videos that you showed me before.
I'd be happy to show one of those. Yeah, this introduction to plant genetics, this was really a fascinating one. So what we tried to do here is to take students through the beginnings of of Mendelian genetics, to have them confront this sort of strangeness of how traits pass through, and sort of experience how puzzling it was when people were trying to figure out how traits are passed from one generation to the next. So this is a bunch of seeds that are called from the Wisconsin Fast Plants Project. So this is a species of Brassica rapa is the name of it, and it's kind of related to I don't know, sort of looks a little bit like broccoli. And they grow to maturity in about, their whole life cycle is about 50 days. And so here we just have a group of them sitting on what's called a seed disc, and you can just observe them growing over a 3 or so day period. And so we asked them to compare seed group 1 and seed group 2. The internet's going a little bit slow, but we can see that, like, these are the same species, but this set looks different. So we just had them have the students like make observations about how do these ones look different. And the major difference is the color of the stems. They have green leaves in both cases, but these have these purple red stems. So we asked the students, what do you think would happen if we took these seeds and planted them, and then took the seed one and planted those. And then when they grow, we take we cross-pollinate them. So we ask, here's, rather than describing it, we say, okay, so this is the same two seed sets that you saw. There's seed set 1 and seed set 2. So you can see right away, these ones have red stems, these ones have green stems. So we let them grow and grow and grow. 2, 3, 4 weeks, cross-pollinate them. Let them grow some more. Now you can see the little seed pods forming on there. They look like little peas. And then that's the end of the plant's life. Take the seed pods off. And so the question is, if you take this seed and plant it, will it have a red stem or a green stem? Or a mix? So we asked the students to make that prediction. What do you think it'll have? And so this is an example where you probably want to use that. Make them record an answer before they see the next. So then we actually take those seeds, put them into a new seed disc, right? And what are the students going to say? Pretty much 100% of the students are going to say, well, there's some were red and some were green. You're probably going to see a mix of red and green. And so they're generally pretty surprised when it's all red. So then we say, okay, let's try another experiment. What if we take these seeds, the offspring of P1 and P2, which are all red, and plant them, but this time we self-pollinate them. So when they get up to their full height, now we're going to just pollinate them from one flower, red stemmed to red stemmed. And we let that grow all the way through. Now all of them were red. We asked them to make their prediction, and they're wrong again in most cases. They're like, well, that's got to be all red. I mean, you had only red stemmed plants. So this is a perfect example of like how to get students engaged with something before you start talking about what do we mean by dominant and recessive. So there's been some really great studies on creating curiosity by having students make their own observations and have them say like, why in the world did that happen? I was really sure that the red stem plant would produce red offspring. And suddenly the green came back. How could that be? Right? So then as a teacher, you're stepping into, well, what if there was this one kind of trait that was recessive and one was dominant? Here's what that would mean. Then what would we have as our outcome? So if you tried to do that in the class, it took us months to do these multiple generations. And so here you can have in 15, 20 minutes, half an hour, students arrive at this conclusion that, wow, plants don't pass traits on the way I thought. So is that what you meant, Tiffany? You wanted to see an example?
Yeah, I just like seeing the time lapse stuff.
Yeah, the time lapse of plants growing are so cool.
Yeah. So there was a question. Yeah. Do you have anything on pulleys? We
don't.
Okay.
Nothing on pulleys. We were getting ready to make one, and we noticed that NGSS doesn't have anything on simple machines. So I mean, we may still. We could make some really cool ones, no question about it. But we wonder if in a few years, as a lot of states move towards either NGSS or things like NGSS, if the need for that will go away. So it'll just depend on teacher demand. If teachers are like, no, we really need that, then we'll add it.
Okay. And then there was a question I did answer. I responded in the chat, but I just want to hear what you have to say. That basically, do you find that students can do pivot labs without like a teacher introducing it, or do they need a little bit of teacher introduction to show them?
Yeah, I think they do, but I think you can. In general, the answer is they need teacher introduction, but you can structure activities so that is built in. So we have, for example, the ping pong ball bazooka, and we're trying to make more and more of these activities like the ping pong ball bazooka, where we really tell them everything that they need to know. We talk to them about how to click on the tools, how to use the video player, how to make sample measurements, and again, using these multiple, so we tell them exactly what steps they should use to control the video and so on. So depending on the students and kind of, are they students that will work hard to get through a set of instructions like this, they could do this on their own. But then you might also say like, okay, I want everybody to just do part one, and then, you know, have a discussion about that, like get on a Google Classroom or something like that, or excuse me, Google Hangout, or have them write on a Google Doc about this part before they go to the next part. But you'll see, again, in this one, very detailed instructions, exactly how to use the data table and, you know, how to reset the stopwatch. So we have a number of activities like that that allow this, that are intended for the students to be able to figure out on their own.
Mm-hmm. And I think if you hadn't already introduced it to your students and you wanted to try to use it at this point in time, you could just use something like Screencast-O-Matic and walk them through, yep, you know, this is how you do that, and upload a quick video that they could watch.
Certainly, I think that would be a great idea to take them through so that they can, you can do things like say, okay, look how I can position this. And mm-hmm. This is a nice one too, because it's so spectacular, because this ball is going so fast that it rips through the pop can, super slow motion. So yeah, I agree, doing, and then showing how like it's easier to measure from the edge of the ball than it is from the middle of the ball, and then how to reset a stopwatch. So you can say like, it's funny, little things that we would often take for granted that students would know. This one, Tiffany, you've used this one?
I have not used this one, but I've used blow dart, the blow dart collision, which is similar in the terms of like, yeah, where to take measurements, when to start the stopwatch.
Start the stopwatch. So we have a lot of students that will put this here, and then they'll say, okay, it looks like it took this long for the ball to reach this spot, not realizing that for most of that time the ball was still inside the tube, so they have no ideas, right? So the idea of zeroing the stopwatch when they can first see the object, resetting the stopwatch. Oh, we're so close to out of time.
Yes, so it is almost 5 o'clock. I want to honor everybody's time. Oh, there was one more question. Are intro pivot labs labeled as such, like labs that could introduce or spell out how to use the controls?
Not as well as they should be. There is a section on the search that's called intro, and they tend to be easier activities, but it's probably something that we can improve on. So you may have to do a little kind of choose the subject area that you're interested in and open up a couple of activities and see if there are some scaffolded ones. That's something that we need to improve.
Okay. Okay. Got a lot of positive comments on the chat. So people saying it was amazing.
Cool.
Yeah. So if there are any other questions, I don't know.
Yeah. So since it's 5, we should stop and say, you know, if you want to take off, thank you so much for coming. We hope it's useful. Use the free trial. Take maximum advantage of it while we have it. Please use our chat, the chat bubble. If you have questions, we're always there. And any questions that you have that we didn't get a chance to talk about, ask away. And we really are doing what we can to help all of you through this, and we think that this can be a very powerful tool. So we hope you'll take advantage of it during this. We really want to try to have your backs to whatever degree we can, because we know you're all in a tough position. So good luck to everybody, and let us know how we can help for you and your students.
Yeah, great. Thank you, Peter.
You're very welcome. Tiffany, can we stay on for a couple minutes, even though it's 5 and people want to go? That's great. But if you have a couple other questions, I would be happy to spend a few more minutes talking. Thanks so much to everybody for coming. Tiffany, thank you so much for organizing this.
Oh, thanks for doing it. It was quick. It was a quick turnaround. You were awesome.
Glad to do it.
I'm going to